Vanakkam. Welcome to this course on biomedical instruments. In this series of videos, we are looking at various types of medical sensors. Many of these are also industrial sensors, but here we are looking at biomedical applications of these sensors, which means that in their design, we need to consider human health and specific requirement of the human health measuring system or physiological measurement system. So far, we have looked at resistive sensors. We looked at strain gauges, thermistors. We looked at capacitive displacement sensors, capacitive sensors. We looked at inductive sensors. In particular, we had a relatively long conversation on linear variable differential transformer, which is an excellent displacement sensor. In this video, we will look at piezoelectric sensors. Specifically, we focus our attention on the piezoelectric sensors that are used in biomedical applications. So, what are some of the measurements that can be made using piezoelectric sensors? But before that, what is the principle? What is the principle of piezoelectricity? It turns out that there are some materials, special materials. These are some special materials that generate an electric field, or they develop or generate electric charge when you apply a force on them. So the material is there and you apply a force in a particular direction, they generate charge. So essentially, they generate electricity. The converse effect is also true. That is, when you apply an electric field to these materials called piezoelectric materials, they deform, they undergo a mechanical change. This type of materials that undergo a mechanical change, when we subject them to an electric field, are used as actuators. But here we restrict our attention to sensors, which are systems that develop or materials that develop an electric field or that generate electricity when we subject them to mechanical loads. So this is the principle of piezoelectricity, or this is the piezoelectric principle. It turns out that the key property of these materials is that it turns out that the total generated charge is proportional to the applied stress or force. So these sensors can then be used to measure displacements. They are also used to measure force. They are used to measure pressure. They are used to measure vibrations. These are some of the physiological parameters that can be measured using piezoelectric sensors. So that means that because they will also they will also generate electricity when placed near the chest, they can be used to record or detect heartbeats, for example. So these materials, these special materials, are used for this purpose. What are the various measurements? Force, pressure, vibration, heartbeats, etc. Some of these materials are naturally piezoelectric. For example, quartz. This quartz is spelled S with an S here. Actually, it's quartz. 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 As a piezoelectric material. There are other materials, Rochelle salts, ammonium dihydrate, lithium sulfate, or some other synthetic or man-made piezoelectric materials. Here is an example of a piezoelectric sensor explaining piezoelectricity. Already we measured this. Already we discussed this. It operates on the principle that when you subject an asymmetric lattice through to a force or a stress or a strain, then there is a charge displacement that happens, leading to development of an electric field. So it induces charges of opposite polarity on two surfaces. This can be measured by measuring the voltage difference between the two electrodes on the two sides. So critically, we already mentioned this, that the total charge is directly proportional to the force applied. The total charge, if you say the total charge is, say, for example, Q, then it is proportional to the force with some proportionality constant D, for example, dF. In this case, in the slide, it is mentioned as Q equal to KF. K is the proportionality constant. And this constant is called as the piezoelectric charge constant. This is the piezoelectric charge constant. And this varies for different materials. And this is something that we can measure. So for each material, there is some particulars. So this system can be assumed to be a sort of a parallel plate capacitor. Then that means I can find its voltage as a function of the force. So that means I can actually relate the force directly to the measured voltage. It's a straightforward process. And it turns out that the amount of charge that is developed for a unit force, for example, is different between different materials, piezoelectric materials. So depending on which application you're using, different materials can be used for different purposes. So again, design consideration. As a biomedical engineer, you need to choose which particular material you will use for what application. Remember, they are highly sensitive to dynamic forces. So that means quickly changing, highly varying, fast changes in forces can be very easily and selectively captured by using piezoelectric sensors. Usually, it requires very high input impedance. But its advantage is also its disadvantage, because it is highly sensitive and suitable for dynamic measurements. It is usually not so suitable for static measurements, because what happens is that once you apply a static force and leave it, what happens is that the remaining charge leaks through a leakage resistor, leading to a sort of a, if those who have worked with piezoelectric sensors will know that there will be a slow drift of the measured voltage. That is happening because charge is escaping. This is why piezoelectric sensors are extremely reliable for dynamic measurements, but are quite unreliable for slow varying or constant or static measurements. They're usually really small, compact, and they're very reliable and robust. We just discussed in the previous slide the amount of charge that is developed per unit force. These are some examples for barium titanate, quartz, PVDF. What you find is that for some material, for example, barium titanate, you are having very high sensitivity and voltage output, but the problem is that they are not very stable. So different materials are to be used for different applications. Usually quartz is considered the reference standard. Barium titanate is usually used in ultrasound measurement. And PVDF is used in wearable systems and acoustic sensors. So some more specific applications of these piezoelectric sensors we shall discuss for a few minutes before we close this topic. A critical application is in the in the problem of ultrasound blood flow monitoring. In this case, the piezoelectric transducers emit 5 to 10 megahertz bursts, and the Doppler shift that is produced, it yields velocity after compensating for any changes in angles. Quite often, piezoelectric sensors are used as intracochlear pressure microphones. They're used because so this material, usually PVDF, really small PVDF discs are used to sense nano level changes in the perilymph material for cochlear prosthesis. That's another application. Frequently, they are also used in MEMS accelerometers, for example, to measure vibrations with a relatively high sensitivity or relatively high reliability. Another more modern application is that these are used as textile or fabric sensors. They are used, PVDF fabric or piezo textiles are used for continuous measurements of the cardiovascular, the cardiopulmonary system, for example. A major constraint is that you need to have high input impedance amplifiers to prevent or avoid leakage and signal noise. Often, almost always, you need to use signal conditioning circuits with charge amplifiers and filters to reduce noise. They are extremely sensitive to dynamic or rapidly changing or sudden, very quick, abrupt changes. So very sudden changes, even though if they may be minute, can be detected using piezo sensors. But that also means that they are quite unsuitable for static measurements. So they are not really suitable for static measurements. And they're usually compact and robust. And, a major challenge is the requirement of a highly specialized amplification circuitry, such as input impedance, charge amplifiers, and so on and so forth. And some of them also have temperature sensitivity. They are not so stable under temperature sensitivity. So most common applications are in the fields of cardiopulmonary or heart sound recording, for example. And they are used as ultrasound transducers, wearable sensors, wearable or fabric or textile-based sensors using PVDF, for example, are now a hot topic of research in this. Quite often, they are also used as catheter tip sensors to measure pressure waves inside the heart chamber, for example, inside the arteries, for example, providing relatively highly accurate and high fidelity data of the heart function, for example. And also to measure respiratory measurement. I mentioned cardiopulmonary, respiratory changes, subtle changes in chest wall movements, for example, can be measured. So they can also be used as part of a loop in rehabilitation robotics, for example, as part of a sensing system of an actuation, robotic actuation system. So they can provide reliable input. Note that they can do this only in dynamic cases. So what does the future look like in this field? And again, as we discussed in the previous topic, miniaturization is the future. Already we have sub-millimeter sized piezo sensors. Of course, look, with miniaturized, with smaller systems, there is going to be a higher cost that is going to be associated. But then if you're going to implant it inside the body, if you're going to implant it inside an artery, you are looking at minimally invasive procedure and implantable system. So cost in such cases is perhaps an acceptable constraint. The other futuristic idea is the use of textile or fabric sensors using PVDF and other polymer-based piezo sensors, so that these are used as wearable systems, wearable piezoelectric sensors, and that can be used for relatively long-term monitoring, for example, in an ICU situation. The other requirement, other idea is, anyhow, we are using high-end electronic systems for processing of these signals because they require high input impedance charge amplification. Perhaps we can also use wireless technology and communication technology to communicate the data digitally via, say, for example, via Bluetooth, for example. This is the future. Yes. So with this, we come to the end of this topic. We'll continue our discussion on other topics such as electrochemical sensors, optical sensors, and Hall effect sensors in future videos. Thank you for your attention.